This lesson is on linear approximation or linearization. Now, before I get into the details of the lesson, a linearization is simply a tangent line. So it's some fancy wording, but every time you see a linearization, think tangent line, and we've been working a ton with tangent lines, so this should be an easy transition. To start off, we have a little box here, and we're going to draw a set of axes, x and y. Next, you're going to draw a generic f of x function. My function always seems to swoosh up. Okay, next, I'm going to locate a point on the x-axis, x equals a, and I'm going to highlight the corresponding point on the graph. Finally, I'm going to draw a tangent line, a linearization, or a tangent line to the function f at the point x equals a. Now, a is what we refer to as center, or the emanating point. It's the point about which the tangent line is drawn. Okay, on our diagram now, I'm going to come over here the best I can and locate the corresponding y value, and that, of course, is going to be f at a. I'm also going to come over here and draw a generic x value. Now, at this x value, I could go up and compute the value of the tangent line at x, and I can also compute the value of the function at x. Now I'm going to mark off here a delta x. And in this unit, we're also going to talk about something called dx. Now dx and delta x both mean the same thing. They both refer to a change in x, but they have different connotations to it. Delta x is used for something that's large or intended, and dx is supposed to be really, really small, in fact, infinitely small. Now, just to give you an example of connotation, suppose in theory I had a son who absolutely loves playing video games, and my son comes downstairs and says, "Dad, please, can I play more video games? Please, Father, Dad, come on." And he asks me over and over and over and over and over again, just hypothetically saying that this is a scenario. Eventually, I get worn down and I say, "Yes, you can play video games." That's scenario 1. Scenario 2. My son comes down. "Father, dearest Father, I have done my chores for a week. I've cleaned my room and done the dishes and did this and that and everything else. I have straight A's in all my classes, Father. Could I please have more video game time?" For which I reply, "Yes, you may." So in both cases, I say, "Yes, you may." The connotation, the language behind the first one was, "I begrudgingly grant you permission." The connotation behind the second was, "I gladly grant you permission." But in both cases, I granted permission. Back to the delta x. Delta x is a change in x. It's a large change in x. Dx is a small change in x. But they both refer to the same thing, a change in x. And I will use them interchangeably here. Now, before we get carried away, we've seen a billion times so far that the equation of a line tangent is y minus f of a equals f prime of a x minus a. And of course you can solve for y by bringing f of a over to the other side via addition. And so this should be oh so familiar to you every time I talk about a tangent line. So I'm going to come down below where I have my tangent line, and I'm just going to label it differently because I'm now calling it a linearization. So I'm going to call this L of x. So that L of x, though, is exactly what I have up here as my y. So L of x is our f of a plus f prime of a x minus a. It's simply an equation of the tangent to the function f at the center x equals a. Now let's put some corresponding y values. If I go to this point up here, I'm trying my best to stay horizontal, then this is going to be f at a plus dx, We could have also said f of a plus delta x. And as I promised, we're going to use those interchangeably. If I come to this point here now, and I draw the horizontal, and here we have L of a plus dx marked off. In this lesson of linearization, there are really two main things we are looking at. First thing, we can approximate the value of the function by using the tangent line. What does that mean? Suppose I'm trying to estimate the value of the function at f of a plus dx. So this point here is the thing or the value I'm trying to approximate. So instead of finding its value, I find the value of the tangent line at that point. So we would say here that L of a plus dx approximates f of a plus dx. And of course it is an approximation, so when we have an approximation, we would have some error there. It's not the type of error that we're going to focus on in this unit, but that is obviously a source of error. And the error is going to be less as the value of x gets closer to a. Well, then our approximation is going to be closer to our real function. And so the idea is as you get closer to a, your approximation is better. Now, the second main thing we're going to focus on in the linearization unit is approximating error. Now, this error is not what we just talked about. This is a completely different error. Suppose I intend to input a, and so the intended output is f of a. That is what is supposed to happen. Sometimes I like to talk about measuring ingredients. Suppose I'm making bread, and an ingredient that helps the bread rise is yeast. Now, I am not a baker, so I'm probably butchering this, but I know that yeast helps the bread rise. So suppose I'm supposed to put in a units of yeast, and the rise is supposed to be f of a. But then we have error here. We have input error. Suppose instead of 1 unit of yeast, I put 1.5 units of yeast. Now, in theory, if f of x models the yield or rise of the bread, this is exactly the rise after the input error. So if I accrue an input error, I get an output error. So this here, delta f, this distance between these 2 points, I'll highlight it here, this distance between those 2 points is going to be the actual error. And what we're going to do is we're going to use the line tangent to approximate that error. Okay, so what does that mean here? Well, instead of using that delta f as the error, we're going to talk about this distance from the line tangent at a plus dx minus f of a. This distance here, which we will call df, that approximates delta f. To come up with a formula for df, I first want to talk about what this value, sorry, let me grab a color, what this value here is on the tangent line. So what I would do is I would plug a plus dx in for x to figure out what this corresponding point is. So here, L of a plus dx is going to be f of a, I'm plugging it into the line tangent equation, plus f prime of a. Now see, if I'm plugging a plus dx in for x, then the a's are going to cancel, and then we simply have dx. So that's this point here. Okay, and then this point here, if I continue this along, we said that this was simply f of a. And then the difference between L of a plus dx and f of a would be the df, which would be an approximation of the true output error. When this is all said and done, there are 2 main things we're looking at. We're saying that f of a plus dx is approximately L of a plus dx. That's the first item we're talking about. The second item we're talking about is delta f, the actual output error, can be approximated with df. So let's define some terms here. A is our intended input. Now I use quotes around intended just to help kind of frame this idea of error. So let's say that's 1 unit of yeast. That's the intended input. Next, I'm going to say delta x. Now remember, delta x is associated with large or intended input error. Now, you wouldn't intend to have error, but maybe you are just curious and you say, you know what, I'm going to put an extra half a unit of yeast just to see what happens. Well, that would be large or intended. Next, the dx, same thing, but it's small. Unintended, we can say, unintended input error. So suppose I wanted 1 unit of yeast, but it was really 1.01 units of yeast because my measuring device is not perfectly accurate. Okay, next, I want to talk about what f of a is. F of a would be intended output. In the case of the yeast, that would be the intended rise. So now we're going to say f of a plus dx, and also f of a plus delta x. They both mean the same thing. What does that mean? Think about it here for a second. That's the actual output from the input error, whether or not it was intended, small or large. That's actually the result. That's the actual rise after we put in an amount of yeast that was not exactly intended. Anyway, delta f. Mathematically, what is delta f? Well, that's going to be f of a plus dx minus f of a. If we come over here, I'm just going to re-highlight that, delta f. And that's going to equal actual output error. It's not the rise of the bread, it's the error rise in the bread. So suppose I wanted it to rise 5 units, but it rose 5.75 units. That would be 0.75 output error. And then df, now this one's pretty cool. df, I'm going to scroll up above here. Remember, df is the difference between the line and the starting point. That's that blue distance, so that's the difference between those two. And so that's going to be L of a plus dx minus f of a, which came out to be f of a plus f prime of a dx. That's this portion minus the f of a. And do you see the f of a's cancel out, giving us f prime of a dx. Let me summarize that here. So df is f prime of a times dx. And what is this again? This is the estimated output error. In our example, that would estimate the additional rise in the bread if we have a given input error, whether it's small or large. Looking at this equation here, I'd also like you to see that if you wrote this as df over dx, that equals f prime of a. If we said like at x equals a. So that makes sense. That's the instantaneous rate of change at x equals a. Say one more time. F of a plus dx is approximately L of a plus dx. Delta f is approximately df, which equals f prime of a dx. And now the examples that we're going to go through are pretty simple, but they really are one of these two types.